Right, we move on to the analytic part of finding extreme values. And we mentioned this briefly the other day, that if I have an area where there is a maximum and a minimum. This is calculus, so we have been talking about derivatives. We are in differential calculus, which is the work with derivatives. If I look at the slope of the tangent line right here, if this is C, then isn't it safe to say that f prime of C equals 0? Yeah. Isn't the slope of the tangent line right there 0? And if I were to come over to D and do the same thing at this minimum, f prime of D is also equal to 0. That is a key thought. So if I know that, how do you think I can analytically find where these maximums and minimums are? I heard a couple people whisper it. Set f prime of x equal to 0. I'm looking for where is the derivative equal to 0. Because at those points, the slope of the tangent line is going to be 0. And there is going to be the possibility of an extrema. I'm not going to say there always will be. All right? So let's write down a theorem. Theorem. If a function has a local extremum at a number C, I love saying that, at a number C, in an open interval. Now notice I said an open interval. Then I know either one of two things is true. Then either, number 1, f prime of C equals 0, or 2, f prime of C does not exist. So I'm going to throw out a term here that you need to learn, and that's called critical points. In calculus, especially differential calculus, when we talk about critical points, we're talking about those possible C values. All right? It's a broad term for the places where extrema can occur. Okay? So, let's work through an example. Get a feel for how this works. Let's say that I have f of x equals x cubed minus 12x. And you are asked to find the maxes and mins. There could be both. There may just be one. There could be one of each. We don't know. Find the maxes and mins on the interval -3 to 5. All right? And sketch the graph. All right? So, first thing, let's find the derivative. This is an easy one. We like easy derivatives. They make us feel good. So we have 3x squared minus 12. There's my derivative. The next thing we need to do, set it equal to 0. So let's do that. 3x squared minus 12 equals 0. Add 12. 3x squared equals 12. So x squared equals 4. So x equals positive 2 and negative 2. Those are two what we would call critical points. Okay? Critical points. Now, what are those places? Those are places where the slope of the tangent line is equal to 0. We didn't have anything screwy going on with this one. So now what we want to do is we've got some endpoints here. We've got negative 3 and we have positive 5. All right? Now, can't I find out what the value of the function is at those places? Right? And we'll try to do this somewhat quickly. F of negative 3. Well, that would be negative 27 plus 36. So that's going to be 9. So f of negative 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, is up here at 9. Okay? And I could also find the other endpoint, f of 5. F of 5, that's going to be 125 minus 60. Yikes, that's way up there. That's going to be 65. I don't even have room for that on my graph. It's way up here. I'll just put a red dot. It's way up here someplace. Okay, it's way up at 65. Now, in between there, I know at 2 and negative 2, the slope of the tangent line appears to be 0. All right? So why don't we find the value of the function at those points? What would, I'm running out of room over here, so what is f of positive 2? F of positive 2 is going to be 8 minus 24. So that's going to be negative 16. So f of positive 2 is way down here at negative 16. Now, let's find f of negative 2. F of negative 2 is going to be negative 8 plus 24. So it's going to be at positive 16. Now, my value at negative 3 was this 9. At negative 2, I'm up here someplace at 16. Now, isn't this a cubic? Right? This is a cubic, so don't we have a general idea now of what this thing is going to look like? Yeah. By the way, does this thing go through the origin? Look at this original function. If I take out an x, don't I have x squared minus 12? If I set that equal to 0, isn't one of the zeros 0? So now I am ready to go ahead and sketch this thing. So I can just connect the dots. I'll get another ugly color and connect the dots, which is going to be up here. I'm going to go through the origin down here, and I'm going to go way up to that point, clear up at 65, way up there. So we have used maximums and minimums, and we even used one 0 point to get us a nice little sketch of this graph, and we didn't even touch the graphing calculator. All right? So let's do another one. Huh? Oh, somebody asked, did we find maximums and minimums? Yeah, we did. This thing right here is a max this thing right here is a min. By the way, if we're talking about local or absolute maxes, isn't this thing down here an absolute minimum on this interval? But this thing right here is not an absolute max. It's a local max. This one way up here at 65, that would be the absolute max. All right? So let's do another example. Let's say that my function is something a little bit more quirky looking, x minus 1 to the 2/3 plus 2. And let's say that we're working on the interval 0 to 9. Well, first order of business, let's find my derivative. F prime of x is going to be 2/3 times x minus 1 to the negative 1/3. And then the derivative of 2 is 0. So there's my derivative. Well, now we need to set that equal to 0. Well, it's probably going to help us to write that as a fraction. Write it as 2 over 3 times x minus 1 to the 1/3, and we're going to set that equal to 0. Now, there should be some light bulbs going off in your head. If I try to solve this thing, don't I have to multiply both sides by the denominator? If I multiply both sides by this denominator, which I don't have room over here, but just pretend I do, that's going to cancel. And if I multiply this side by the denominator, well, that's going to be 0. And I'm going to have that 2 equals 0. Well, 2 doesn't equal 0. So guess what that means? There are no values where f prime of c equals 0. That's what that means. All right. So what would I do now? Well, let's check my endpoints. All right, because we're still trying to get to a graph of this thing. What would f of 0 be? Well, f of 0 would be 0 minus 1, which is going to be negative 1 to the 2/3 power. So that's the cube root of negative 1 squared, or the cube root of 1, which is just 1. So this is going to be 1 plus 2. So f of 0 equals 3. All right, there's one endpoint. And how about f of 9? Well, f of 9 is going to be 9 minus 1, which is 8. The cube root of 8 is 2. 2 squared plus 2. So 4 plus 2, that's going to be 6. But there's one other thing that we have not done yet. There is another critical point. And when we are looking for critical points, we are not just looking for where the value of the derivative is equal to 0. We are also looking for a place where the derivative might not exist. Here is my derivative. And didn't we rewrite it right here? Is there a place where that derivative does not exist? 1. Okay? If I put a 1 in right here, don't I get a 0 in the denominator? So x equals 1 is another critical point. Now, it's not a maximum or minimum because we found out there's no places where the slope of the tangent line is equal to 0. But we can go ahead and plug it into the function and see what happens. All right? We've got 2 points down here. We've got f of 0 equals 3. We've got f of 9 equals 6. Why don't we do f of 1? f of 1 is going to be 1 minus 1 to the 2/3 plus 2. It's going to be 2. So now I've got three values. I've got f of 1 equals 2. I've got f of 9 equals 6. And f of 0, didn't that equal 3? Right? So look what I've got if I sketch a graph now. I'm just going to plug those points in. F of 0 equals 3. So there's a point here at 3. F of 1 equals 2. And f of 9, 2, 3, 4, 5, 6, 7, 8, 9, equals 6. So what do you think happened? Now, don't I have a maximum and a minimum? What do you think happened right here? What, if I wanted to draw a graph, what do you think that is? What does it look like it could be? A cusp. That's the place that we found out where the derivative did not exist. Okay? So when you are doing these problems, as you're looking for critical points, you must also consider places where f prime of x does not exist. Okay? That can also be a critical point to help me get my maximums and minimums. Now, we didn't label them here, but it's pretty obvious. This is my max, right? And this is my minimum. Even though it's a cusp, it's still the minimum on this interval.
It's not the absolute.
For this interval, yeah, it would be absolute. Okay? This thing over here, this thing right here, could be a local max. Could be a local max. That's right. Okay, let's do one with the trig function, because I think you're going to see some of those. We're running out of time. So if you get one that is like this, all right, and I take I find the derivative of it. Well, I'm going to have f prime of x is going to be 2 cosine of x minus 2 sine of 2x. I did use chain rule over there. I just kind of did it quickly. Now, if I want to look, oh, and by the way, let's say that we're looking at this on the interval 0 to 2 pi. Well, what am I doing? Well, I'm setting this thing equal to 0. 2 cosine x minus 2 sine of 2x. Now, there's a couple different ways that you could tackle this problem. One way is you could add this 2 sine of 2x to both sides. And you would have 2 sine of 2x equals 2 cosine of x. And you could divide both sides by 2, and now you've got the sine of 2x equals the cosine of x. And so you could say, where are sine and cosine the same? There are places where that's true. Where are sine and cosine the same on the interval 0 to 2 pi? Well, what is the sine of 45? Or pi fourths. Isn't the sine of pi fourths radical 2 over 2? And the cosine of pi fourths is radical 2 over 2, right? So there's one place, right? But wait, look what that is one, that's the answer to this. Okay, so I know that This one would be 2 times. This needs to work, this thing right here needs to work out to be a pi fourths, right? So in reality what you do is you set 2x equal to pi fourths and solve it. So that value would be x equals pi eighths. Okay, so we'll finish talking about this problem some more tomorrow, but that kind of gets us started on looking at those values, and we will stop there for today.